Yeah, it works. Okay, thank you. Yeah. Well, thank you very much, Susan, for the invitation. It's really a pleasure to indeed escape Chicago weather at this time of year and take a break in sunny California. So yeah, it's kind of my pleasure to give this talk. It's a somewhat emergent area of mathematics. It kind of appears in these sorts of things that you see in nature, flocking of various birds, fish, swarming of insects. It also appears in kind of a more technological applications like decentralized control of various vehicles or robots, or satellite navigation applications. Of course, these are vast, these are very broad areas in applied science, and there are models that are designed to have some kind of a predictable power behind each phenomena. But as mathematicians, we always like to kind of extract some core mechanisms from these complicated models and try to understand them, sort of get to the bottom of the mathematical structure. So what we're going to discuss today is the class of models called alignment models or flocking models, where the basic basic driving force behind the dynamics is an alignment force. So typically it's on a discrete level, it's an agent-based system, a second-order system, where the velocity is trying to adjust itself to some kind of an average velocity of the agents or species around the given one, and trying to become less like itself. So more like the average around, but less like itself. So it gives rise to this alignment force. And SI typically is some kind of a communication strength, which measures how strong is connection between the agents around a given one. So this phenomenon we call emergence can be sort of described in general terms as emergence of some kind of patterns out of random initial condition via only local interactions. Okay, so one would expect that agents, when they talk to each other and try to adjust their velocities to the average of the neighbors, will probably form some kind of coherent clusters around themselves, which then in time will evolve into globally aligned or coherent motion. The aligned state is not the only collective outcome. Of course, you can see we've seen of schools of fish which swirl around. So these things are, of course, possible to build into these models, but they require more complicated forces to be added. Okay, so we would like to study just the core mechanism of alignment and understand how this particular pattern appears out of the system using only local interactions. Okay, so we kind of narrow down this problem to this particular issue. So one of the first models that appeared, models that are possible to analyze mathematically, were due to Cucker and Smale. So it's a very simple but natural communication protocol. Here, the communication strength is regulated by this kernel, okay, which is just a radially decreasing kernel. And it just tells you that if the agents are far apart, the communication is weaker. If they're closer to each other, the communication is stronger. Okay, as simple as that. So you can actually kind of put it in the framework of previous slide by kind of factoring out this sum of influences of other agents out of this sum, and then forming this averaging protocol and this strength function. Okay. So the reason why this model has become so popular is because, unlike previous models where alignment results were based on perpetual assumption of connectivity of the flock for all time, which is a hell lot of an assumption, this Cucker-Smale model required only certain conditions on the kernel, okay, and not on the actual positions of the flop. So they distinguish between two types of kernel, local kernel and long-range kernel. Local kernel is the one that governs only local interactions, right? This is where the problem of emergence becomes. Long-range kernel is the kernel which has long tails, and one can quantify the strengths of this long-range interactions by, for example, imposing some kind of power law at infinity. So what they proved is that if this power law is non-integrable, all right, so it has some weight, okay, it doesn't decay too fast, then there's enough communication between agents to be able to prove that for any initial condition, the system will flock towards some average momentum, which is conserved, by the way, for this system. So it's a predictable limiting velocity, and the diameter of the flock will remain bounded. All these quantities are quantifiable. The rate, the exponential rate, and the radius of diameter is quantifiable in terms of power beta. So that was kind of the first very powerful result with very simple condition on kernel, and it has gained a lot of momentum later. So it was extended to kinetic version by Carrier and others, 2010, and macroscopic or hydrodynamic version by Tan and Tadmer. So speaking about strictly local interaction, now the problem is focused on the local interactions only. If we're looking at open environment, which is of course a natural environment to study these biological systems, it's actually easy to construct a counterexample. Just put one flock far away from the other flock and shoot them in opposite directions. They will never communicate, right? They will never come close to the communication distance, so they will never align. So therefore, this connectivity condition of the graph becomes important. So as long as they stay connected, then in fact, it's possible to prove alignment even with only local interactions. Morales, Pezhik, and Tadmer proved another result. So this is the assumption for all time. So it's a big assumption. But if your communication strength is very, very high and initially the flock is connected, then it will remain connected for all time because it essentially will never move. Essentially, it just instantly aligns and kind of crystallizes. Now we can study flocks with confinement force, which keeps it together, which is actually a natural force in many of these biological systems. Or just to kind of simplify the settings, which we can just put ourselves on a compact manifold like torus, pretend that we're studying flock somewhere in the bulk, like we do in fluids, right? Put the conditions sort of like a fluid in the bulk. And then here the problem is still, there is a counterexample because you can put one agent on one geodesic and the other agent in a perpendicular geodesic or even parallel geodesic, but far, the communication distance away from this. They will never meet, right? If their velocities are mutually rational, by Kronecker condition, they will never come close to some distance. Therefore, they may never communicate. So that's another counterexample. So these are called locked states, okay? These are highly unlikely to occur because they form kind of a measure zero set in the ensemble of all initial conditions. So they're very highly unlikely to occur, but they do exist. So how do we deal with this? Well, okay, so let me first of all tell that this has a lot of applications. So people apply this for, like I mentioned, for the synchronized flight of satellites. There was a European Space Agency commissioned a project to launch a few satellites in space and take pictures of some habitable planets. And those satellites have to be synchronized in a certain way. And some engineers computed that if the Cucker-Smale protocol is to be implemented, then this power beta has to be equal to 0.4. So that's a very specific number, which is the most economical from the point of view of energy required to synchronize these satellites, and yet provides sufficient level of synchronization. There are all kinds of other applications to decentralized control, to optimization problem, and the system have been numerically studied by using machine learning technique to try to adjust the communication kernel to the specific biological experiment. So it's been, it has seen quite a success. So when we study a lot of agents, then it makes sense to kind of pass to the limit, right? The mean field limit of these empirical measures and try to understand the continuous distribution of agents. So that's a typical idea of statistical mechanics. Because when the number of agents is large, studying ODE is very, very complicated, but they turn out, this distribution of agents turn out to converge in most cases to some kind of a continuous probability distribution, probability density F, which satisfies the corresponding loss of kinetic loss of alignment model.
Is there a minimum number of elements so that you can call it a cluster? Like how do they form?
It actually depends. Okay, so it depends on the particular applications. For example, I'm not a biologist, but I know that
when do they happen? Like I'm trying to imagine fish starting to swarm around, you know. So at first you have 2 or 3, and then they increase, and then
so it's in the order of hundreds already. So, but it's interesting that in the case of, for example, starlings, European starlings, they see only 7 birds around. So their communication is really local, and yet they form this fluidy motions of flux, which is actually a PDE motion. Okay.
And is there a study of like the evolution from very little number, very small number to large number? Because they could increase also, the number could increase with time.
Yeah, but then you change it. Yes, there are such studies, of course. These are studies more relevant to multiplication of cells on embryos, for instance. So biologists are very interested in that. But it's mathematically quite challenging because you have to change your dynamical system as you do that. Yeah, that's a good question. Yeah. So, but typically, if you just study kind of homogeneous agents, right, of equal, actually, it doesn't have to be equal masses, but it just simplifies analysis a lot. You can converge to a kinetic model, and if you put, if you look at these macroscopic variables, the density and momentum, then you can formulate this alignment force as the alignment of the kinetic variable to the average velocity, where the average, the averaging operator, we call it environmental averaging, has to satisfy certain functional axioms. But in this particular examples that I mentioned, the Cucker Smale, it looks like this. So it's a convolution of the momentum with the kernel divided by the convolution of the density with the kernel. There are other variants of the Cucker Smale model that appeared, and for all of these models, you can still justify this limit. So there's a Moch-Stadmer model where this communication strength is equal to 1, and there is a new one that sort of modifies one more time Moch-Stadmer, and that extra modification appears to have very, very good analytical properties. So there's sort of I posted a recent paper on how this can be done systematically. It's on the archive. It's called environmental averaging. So you can consult that for details. So when you try to read off the hydrodynamic model, you take first momenta of the kinetic model, and then you arrive at what's called the Euler alignment. So Euler alignment system has the classical conservation of mass equation and also conservation of momentum. The alignment force appears to be like a continuous analog of the discrete one, but the problem here is that we have this Reynolds stress, which is the classical problem in this transitions from kinetic to hydrodynamic. This extra Reynolds stress tensor is not expressible in terms of macroscopic variables. So there's still this probability distribution sticks in it, and your kind of next step would depend on your particular modeling scenario, how to get rid of this tensor. So one of the modeling scenario is to enforce local alignment. So this was done by Kahn and Vasseur for the system without the alignment force. And then Figali-Kahn settled it with the Cucker Smale alignment, but no vacuum condition. And I extended it to the general flux. So you can actually see that if the local alignment force it pushes the probability distribution to monokinetic ansatz. So where the distribution is concentrated on the macroscopic velocity at every spatial variable. So in this case, you arrive at a pressureless Euler alignment system where the radial stress is equal to 0. There's also another scenario where you enforce local alignment plus diffusion. We'll talk about it a little bit later. Okay, so so we covered kind of various levels of description. Now, what can we do with this problem of emergence? So suppose that you have just a local kernel. The only information you have is that it's bound from below on some little ball. So as I mentioned, there's a problem of locked states, right? And one can think of various scenarios how to get rid of this. So one is to impose some kind of connectivity condition, right? In a classical way. On the hydrodynamic level, this means that we are imposing some kind of lower bound on the density. Okay. What is that minimal requirement of density we can make in order to still prove alignment? So that's question number one. Question number two, if we get rid of this locked states by disrupting them with the noise, okay, that's a natural thing to do. In fact, in many systems, in many models of collective behavior, there's always a noise added to it because it sort of kind of takes into account certain level of uncertainty. The stochastic noise will definitely destroy these locked states. So then the alignment problem can be understood as a problem of relaxation as you let time go to infinity, right? Where will your probability distribution converge to? What kind of equilibrium as time goes to infinity? So this is where this hypocoercivity methods come in the picture. And the largely unexplored area here is the generic initial data. So completely deterministic discrete case, can we say that for almost every data, this does not happen? So almost every initial data will result in the aligned state. It's a very wide open, so it's called generic alignment conjecture. It's wide open, but it's recently has been settled for the number of agents equal to 2. So I'm not ready to talk about it in detail, but it is already, there is some progress in it. So let's just kind of start with this first idea of connectivity. How much connectivity do we need? So if you just look at the energy estimates, okay, just basic energy. This is your energy. Suppose that the momentum is equal to 0. We can always translate it to 0 by Galilean invariance. So by saying that the energy tends to 0, we're essentially saying that it flow converges to the mean velocity, right? So we're interested to see when does this energy go to 0. So the energy law, just like for Navier-Stokes equation, although here we actually have equality, and Trevor proved the Sansager critical results for energy conservation, but this is not what I want to go into at the moment. So let's just argue formally. You have this energy identity. Your diffusion here comes from misaligned velocity. So as long as velocities are misaligned, they burn energy. Okay. So if you remove these densities of which you have no control at the moment by lower bound, you have this just a variation integral. So it actually turns out to be equivalent to distance, L2 distance of velocity to its mean value. Okay, but this is the energy, right? So you have to just reintroduce the density by putting it back in and divide it by its maximum. So at the end of the day, you recover your energy by cost of this expression of the density. So rho minus is the minimum of the density, rho plus is the maximum. So that was in essence, the result of Tadmer in notices. So you prove that if this quantity is divergent in time, then the energy will go to 0, so the flow aligns. So now if you ask yourself, what is the connectivity condition that is necessary? So suppose that if the rho plus is under control, then you need something like 1 over square root of t for the density to be bounded from below, right? So there are two problems with this result. One is that none of this is known to hold in any situations. So it's really an assumption for all time, right? You can actually get rid of the rho plus by cost of increasing the power on rho minus. This is something that was done recently. So if your kernel happens to be Bochner positive, so if it's a convolution of another positive kernel with itself, which is not that restrictive if you think about it. Well, all I'm saying is that the Fourier transform of phi is a positive function. Okay, just positive value. Then you can actually replace this condition with rho minus to the fourth. Okay, so this comes in this general context of environmental averaging models. You have to look at it from kind of bird's eye perspective, and you realize that Cucker-Smale averaging is positive definite in a quantifiable way if the kernel has the structure, and that allows you to calculate the spectral gap, which is essentially what we're doing here, without the use of the upper bound of the density. We'll come back to this result a little later. So, well, what do we do with that? In the case of this, the classical communication, which kind of takes into account just Euclidean distances between agents, that's the best thing you can do. But it turns out that in a lot of applications, and there are some field studies, like real biological observational studies that have been done before, in particular under the Star Flag project by a group of Italians, which observed that you know, a lot of the systems, the species, they don't feel Euclidean distances, they feel densities of the crowd. Okay, so if there is a lot of birds in this direction here, a cumulation of birds, then the communication goes slow in that direction because you have to kind of go through or observe a lot of birds. Whereas if in the other direction there are just a few birds, then I can easily, you know, 2 or 3, I can easily average their momentum and, you know, try to adjust it. So it's not really that the metric distance that is important, it's the topological distance, the distance that is actually dependent on the density of the mass. And so we tried to model this scenario. So we postulated that between any two agents, there is some kind of region of communication. Doesn't really, for the purpose of analysis, doesn't really matter what shape it has. It only matters that there is a less than 180 degrees angle, because it's kind of related to the angle of view of an agent. You can define the topological distance as the mass of this communication region. The mass, of course, involves the density, which depends on time. So this topological distance changes in time. So it evolves as density changes. And so we can build it into the communication protocol as inversely proportional to this distance.
Is it a distance?
No, it's quasi-distance.
It's just a name.
It's just a name, yeah. It is distance at 1D, but it's just quite, yeah, good observation. We call it distance, but it's actually not quasi-distance. I mean, inversely proportional, because if the region is heavy, okay, I want my diffusion in that direction to be slower. If the region is light or thin, I want the propagation information to be faster. So that's why it's inversely proportional. And there's also some metric component that is left there. So we're kind of dealing now with the singular kernel, which is like, it scales like the kernel of the fractional Laplacian. Turns out that this makes this model pretty complicated to analyze in terms of regularity, because you have an active kernel which changes with the density in a singular way. But as far as alignment, it gives a much better result. So you only have to assume that the density is bounded from below by 1/t without any assumption from above. Okay, 1/t. In that case, you can even get some rate of alignment, so something like 1/log to the power 1/6. And it turns out that in 1D, this is not an assumption. That actually holds automatically. You can prove it for any non-vacuous initial condition. So in 1D, it becomes an unconditional alignment result. So we're kind of hopeful that these topological models may evolve someday into, maybe not exactly the one we introduced, but maybe there's another modification necessary in order to apply it in multi-D. I mean, this is true in multi-D, but it's still in dimension bigger than 1. This is a requirement. Maybe there is a result sometime in the future, which will hold without any requirement. But the regularity theory of this model, topological models, is quite technical, and I will not even attempt to give you the details. This latest paper with my students and postdocs, we had to apply this para-differential calculus in order to prove local existence, really. But it has to come with some sharp continuation criteria, which allows us to prove global existence in some specific multidimensional settings, like unidirectional flows or things like that. So let's now move to the second part, where we are trying to put the noise, okay, and disrupt those locked states using the noise. There are many ways you can put the noise in the system. So the one that we found the most natural is where it's kind of weakly multiplicative. So you put some weight in front of the noise, which scales like square root of the strengths. Okay, so the strengths here is SI, and this scales like square root of SI. Why do we do that? Because on the using Ito calculus, you know that this will scale like a square on a kinetic level, right? So the stochastic mean field limit will produce this Fokker, which we call a Fokker-Planck alignment equation, which now has a diffusion in the V variable, which has the same weight in front of diffusion as it is in front of the alignment force. And that's good news because this equation has a good equilibrium, the global Maxwellian. So now we would like to study what is the limit as time goes to infinity of the distribution F sigma if we start with an arbitrary initial data. So that's the typical global relaxation question. So if we are successful at establishing this, then in the limiting in the Venetian noise limit, I wanted to say Venetian viscosity, but it's actually very similar to that. In the Venetian noise limit, you will recover your perfectly aligned state, right? Because the Maxwellian would converge to Dirac, so concentrated at the momentum. So it actually, this is how we understand laws of turbulence, right? We take time, we take some statistical quantity, like for example, a structure function, right? We study first long time behavior, let the dynamics settle on the attractor, and then we try to understand what happens in the statistics when the viscosity goes to zero. Of course, Navier-Stokes is much more complicated because the attractor is much more complicated. Here, the attractor is just the Maxwellian, okay? But it's the same philosophy. Actually, there are more connections with turbulence than this one in this subject. So this program has seen partial success in the beginning. So in 2010, Duan, Farneiser, and Toscani looked at the Cucker Smale, and they proved that same result, the relaxation, but in perturbative settings. So if you are already very close to Maxwellian, you do the linearization analysis, you establish stability, spectral stability, and you show that it has nothing to do but just to fall on into the equilibrium. So for small perturbations, that's true. If you look at not Cucker Smale, but the just pure local alignment model with macroscopic loss to U, then that's also true in perturbative settings. So these techniques of this result were inspired by collisional models, in fact, that came from successes for the Landau and Boltzmann equation by Gu and Duan, using this nonlinear energy estimates. So, but they're powerful methods, but quite restrictive. So it's only the sort of small initial data results, so to speak, near the equilibrium. So the first global result came for this kind of modified Moch-Stadmer model, where you have this Emergence, special Emergence protocol. So here you can establish regularity theory for the corresponding kinetic model in this weighted Sobolev norm, Sobolev spaces. And the result comes still with the global assumption on a macroscopic field. So if you work with kinetic equations, you know that you don't get a priori good bounds on macroscopic quantities. So you only know that the momentum is finite, and you know that the mass is finite, but you don't know if the macroscopic velocity is bounded. And that's the problem in the Boltzmann equation, Landau, and all these collisional models. The same problem here. We cannot establish this a priori. A lot of results for collisional models are based on using these assumptions. So here we also resort to this assumption. So if your observable macroscopic field is bounded, so there's no critical things happening, then yes, indeed, your distribution will relax to the Maxwellian. Okay, with this particular rate, sigma to the power 1/2, which is maybe not the most optimal, because we know from this enhanced dissipation result that it should be maybe sigma to the 1/3, but we were not after the optimal rate. All it mattered to us is that it does relax to the correct limit. Well, going back to Cucker-Smale, so why is this assumption necessary? Because I want to control. So this field here depends only on x. So essentially, this is just a transport term along the v, right? So a lot of results a lot of estimates in this relaxation technique rely on the boundedness of this drift, okay? And I cannot prove that, so I have to assume. Now, if you look at the Cucker-Smale and you kind of spell out, what are the terms in these forces, you can see that there is nothing here that is unbounded, okay? This is the momentum. We know it's a priori bounded by the energy, and the energy is uniformly bounded for all time. So the filtered, the modified momentum is going to be bounded, of course. So is the rho phi. But the problem is that you have this now extra term in front of the noise diffusion. So this can degenerate. In principle, it can go to 0, and that will degenerate the diffusion in that particular region of space. So that will prevent me from proving the relaxation. Well, it turns out that, and here comes this Bochner positivity condition again. It's a magic condition. If it is Bochner positive, then everything works. The model is globally well posed for any initial data. Moreover, starting from some positive time, it gains positivity everywhere. Okay, it's the known effect for Fokker-Planck equations, but it's difficult to prove it for nonlinear Fokker-Planck equations. For Kolmogorov Fokker-Planck, it comes from just the Green's function. Here we have to say a lot more about it. So the density gains weight everywhere, and it will remain uniform for all time. So it means that my condition with this one, with rho minus to the 4th, works. And by the way, I don't know anything about rho plus. I don't know anything about the supremum of the density. And I don't need it if I am Bochner positive. Okay? So it will gain the density, and it will relax to the Maxwellian with the same rates. Right? So this is a completely unconditional result. You start with any distribution f, and it will relax to the Maxwellian. It may actually take a long time, because there will be some transitional periods, because especially if you start with a compactly supported, it may wander around the kinetic space until it kind of settles on this bell-shaped distribution. It may take a long time. Well, it depends on sigma. See, it badly depends on sigma. Okay, but it will eventually. So there are quite a few ingredients in this proof. First of all, the proper way, we need to prove well-posedness and continuation criteria in a certain way that relies only on the lower bound of the density. Like I said, we need to establish uniform gain of positivity. These solutions to these equations tend to gain Gaussian tails. So because they try to mimic the equilibrium they converge to. But the difficulty is that you have to prove this for any positive time. And these constants A and B have to be independent of time. Because then the integral over V, which gives you the macroscopic density, becomes bounded away from 0. So you stay uniformly away from the vacuum. Then we have to establish that these, okay, so spectral gap related to only in terms of lower bound on the density. And then we have to run the Villani, de Villiers type of hypocoercivity estimates in order to prove that this uniform spectral gap leads to the proper global relaxation result. What's curious about this step here is that typically these estimates, they work well for linear models. For nonlinear models, they require some kind of smallness condition, some kind of small, like for example, Fokker-Planck Poisson requires smallness of potential. And but here it's a fully nonlinear equation, but still due to certain constellations, this kind of linear method works in full nonlinear equation. So I will probably just sketch a little bit the details because the details are quite technical. We sort of use the Villani notation because it's very convenient and actually very insightful to rewrite your Fokker-Planck equation in terms of this renormalized distribution. So F divided by mu. And then you can see that there is a sort of the symmetric way of writing the diffusion part, X transport part, and then also this alignment part fits nicely in this framework. So the way you measure the distance between your distribution function and the Maxwellian is through what's called the relative entropy. Okay, so in terms of H, it looks like this, H log H. So if you have a dissipation of entropy, if the entropy decays in time, then you're in the game. So then you have a hope to prove that, just like for Boltzmann equation, the H theorem, right? Once you have the H theorem, you have a hope to prove relaxation. So we do have this law. Actually, we have two forms of entropy law. One is actually non-dissipative, and it's in fact useful. So you just do it as for Fokker-Planck equation. You have this what's called the Fisher information. Okay, this is your dissipation in V, but you also have this residual energy coming from the alignment term. It's a nonlinear term, but unfortunately, it has the wrong sign. It has a positive sign. This has a negative sign, so it dissipates this one. So this is in general non-dissipative form. So, but there is a dissipative form where you kind of sacrifice the Fisher information and just write it all in terms of macroscopic energy. Okay, so it does give you dissipation, it gives you control over the entropy for all time, but it completely loses the coercivity, right? Or even hypocoercivity, because it has no information at all left in the V direction. So the idea is to combine these two forms of the entropy law by using the spectral gap. So if I know that this term is not only negative, but quantifiably negative, okay, less than lambda times the scalar, the basically L2 norm of U, and if I can quantify this lambda, which is the spectral gap of the averaging operator, then I can assume that it's actually bounded away from zero for now. Then you can combine these two terms and kill this residual energy. Okay, so you will actually gain both the Fisher dissipation and the energy in your entropy law up to a constant. And then, like I mentioned, you apply the Villani-de Villiers method. So you try to restore the coercivity of the dissipation. So you only have it in V, so you want to actually restore it in X direction as well. And the way to do it is to complement your partial Fisher information with the missing part, which is the information in X variable. And also what's crucial is the mixed one. So the mixed one is doesn't change really by the Young inequality, doesn't really change the full information, but the addition of this epsilon cross product term allows you to use this mixing with the X transport term to pump information from V to X and back. So this is not, I mean, this is the at the heart of all this hyperellipticity, regularity results, and so on and so forth. But here we're talking about long time existence results. So we have to make sure that when we do these estimates, the constants are independent of time or depend algebraically in time. And at the end of the day, we collect the information, which is basically second derivative of the entropy, combine it with the entropy equation to get some kind of Grodal estimate. So the Grodal estimate will give you exponential decay of the relative entropy, and by Caesar-Kullback inequality that controls the L1 distance between F and the Maxwellian. So this is just in a few words how this proof goes. Of course, the details here are quite technical. So the last thing I wanted to say is how does this spectral gap estimate come into play? So the thing is, or this Bochner positivity thing. So if you look at the Cucker-Smale scalar product, you have an expression like this. Okay, unfortunately, if your kernel, even if your kernel is positive, you don't know whether this product is positive. But if it's Bochner positive, so phi is the convolution of psi and psi, you can move one psi to the u rho, and then you get the square. Okay, so now you see it has a positive sign. The question is, can we say something better than zero? Okay, and that is the interesting new inequality that one can obtain. Not only is better than zero, it's better than zero quantifiably by this specific. This is how it depends on the lower bound of the density in this very way. If you unwind this inequality in terms of the lambda, then you get this result. So if you establish gain of Gaussian tails at infinity, and if you find that this A and B are independent of time, then you're done. The density is bounded away from zero. You have a uniform spectral gap. Villani works. Okay, and this is excruciating result to prove. Why? Because, well, I mean, it's not new result. I mean, we know it for Fokker-Planck equation, even for Landau equation, it was proved. But all those results give you constants A and B that depend on time, and they actually deteriorate. They kind of give you false alarm. They raise the tails, and then the tail go down slowly. So you just don't control because these constants, they depend on all kinds of stuff. And it's particularly on regularity of solutions, and the regularity for Landau deteriorates in time. Here, the technical issue was to show that these constants A and B depend only on the entropy. Okay, and the entropy is the most basic thing you can control because it's decaying. So therefore, constants do not deteriorate. So it involves a lot of barrier constructions and this construction of Harnack chains using weak Harnack inequality for super solutions. And this was not possible if not for these new results that just came last year, basically, by Ancheshi and Zhu, who did it for Fokker-Planck equation in terms of construction of Harnack chains, and the weak Harnack inequality by Jessica Kuran and Cyril Imbert, very smart people, who extended the weak Harnack inequalities in the weak sense, but for super solutions, which was very essential for our settings. So this is in a few words how it goes. There are some there's a nice paper by Eitan Tadmer where he surveys this subject, especially on the macroscopic level that I mentioned in the beginning. I published a book recently which talks about things extensively and systematically. And there is this kind of new framework where this Bochner positivity comes into play. This was posted on the archive recently. So these are references for my talk today. Well, thank you for the attention.